Hello, Professor. My name is Zhichao Sun, and this video is to explain the question 1 for homework 10. For the first question, told us that from the lecture notes, collects the definitions and simple properties. Probability, masses, or density mean autocorrelation and autocovariance of example of stochastic progress. First, the person progress. For the person progress, first in the number in the range of t1 to t2 of the points tr in the interval t1 t2 of length t equals to t2 minus t1. It's a personal random variable with parameters lambda t equals to lambda t. So the probability of n t1 t2 equals to k is it could be rewrite like that. So the second, if the intervals t1 t2 and t3 t4 are non-overlapping, then the random variables n t1 and t2 and n t3 and t4 are independent. So we could see it from this picture. And for at a time moment t, there is no more than one person point using the point ti. We form the stochastic progress of xt into the equals to n0t. First order probability masses, the probability of xt equals to k is right like that. And the mean equals to lambda t, and the autocorrelation equals to this one, and the autocovariance equals to this one. Equal to this one. And for the second part, it told us the Purcell increment. A Purcell increment defines as y equals to this one, and the xt is the person progress. First order probability masses is that like this. We let the t equals to epsilon, and the mean equals to lambda, and the autocorrelation equals to this, and the autocovariance equals to that. For the second part, Purcell impulse. Purcell impulse process is defined as zt equals to the degradation of xt, where xt is person probability masses, no definition. Then the mean of this one is lambda, and the autocorrelation is like this, autocovariance like that. For the fourth part, the semi-random telegraph signal. Semi-random telegraph signal xt is defined based on the person points again, then the number n t1 t2 of the points ti in the interval t1 t2 of the length t equals to t2 minus t1 is a person random variable with parameters lambda t, and then the probability could write like this, and the xt equals to 1 when k is even, xt equals to -1, -1 is k equals to odd in this one. First order probability masses is could be rewritten like this one, and mean is this, autocorrelation like that. For the 5, random telegraph signal. Random telegraph signal yt equals to a multiple xt, the p a equals to 1 equals to p a equals to -1 equals to half of half. Where xt is semi-random telegraph signal, so from question 4 we can write this like that. We use the absolution to redefine this equation. For the sixth part, random work. Random work tells a fair coin n times. K is the number of hands in n tosses, and nt equals to ks minus this is that, and the probability could be read like this one. the mean equals to 0, autocorrelation is the minimum of n m equals to multiple the power of s, and the autocovariance is read like this one. For some part, the Wiener process Wt equals to the limitation of xt when t prior to 0, and this to a, and this n it tends to the infinity, where xt is the real number. First order definition function could be read like a Gauss form, and the mean is equals to 0, and autocorrelation is the mean of t1, t2 multiple alpha, and autocovariance is like this one, the meaning of t1, t2 multiple alpha.